Hello. Logarithms, I think, have a reputation for being this obscure and complicated mathematical topic, but really they represent something fairly simple. And in this video, I'm going to try to explain what that is and why we care about logarithms. But first, let's take a look at the word. Where does the word logarithm come from? Well, it's made up of two parts, log and rhythm. And log comes from the Greek word logos, which is also where we get our word logic, as well as words that end with L-O-G-Y that indicate the study of something, like psychology, geology, archaeology, theology, things like that. And then the rhythm part of the word comes from arithmetic, and maybe also algorithm. Now, before I tell you exactly what logarithms are, let's start with a kind of a trick. Here's a list of numbers that has a special property. You can take any two numbers on this list and multiply them together, and you will always get another number that's also on the list. Now, you are totally welcome to try this out for yourself. Pause the video if you want, and pick a couple of numbers on the list and multiply them together and see if you can find the result also on the list. But let me show you an example. So we can take the number 2,187 and multiply it times the number 1,594,323, and let's see what we get. Okay, so 2187 times 1594323 equals 3,486,784,401. And oh, look, there it is on the list. Now notice we took the 7th number times the 13th number, and what we ended up with was the 20th number on the list. Those little blue numbers allow us to refer to which number on the list we're talking about. So when I multiplied the 7th and 13th numbers together, I got the 20th number. You notice the relationship there. Yeah, 7 plus 13 equals 20. So if I'd known that, I could have predicted what the result was going to be. When I multiplied the 7th and 13th numbers together, I was going to get the 20th number on the list, the number next to the little blue 20. Now, this also works with division. I can take any number on the list and divide it by any other number on the list, and the result will also be another number that's on the list. Again, you can try this for yourself if you want. You're welcome to pause the video and try it out, but I'll do an example. We'll take the number here, 43,046,721, and we'll divide it by 729. So 43046,721 divided by 729 equals 59,049, which, there it is, it's on the list. Now notice we took the 16th number and divided it by the 6th number, and what we ended up with was the 10th number. And 16 minus 6 is 10. So I could have predicted what the answer was going to be just by subtracting those little blue numbers. Now here's why this works. What's special about the numbers that make up this list is that they are all powers of 3. The first number on the list is just 3 itself. That's 3 to the first power. Then comes 9, which is 3 to the second power, 3 times 3. Then 27 is 3 to the third power, 3 times 3 times 3. 81 is 3 to the fourth power, 3 times 3 times 3 times 3. 4 3's multiplied together, and so on. So the little blue numbers tell you what power of 3 you're looking at, how many 3's you have to multiply together to get that number. And then when we multiplied together the 7th and 13th numbers on the list, we were multiplying together 3 to the 7th power times 3 to the 13th power. And if you know how exponents work, when you multiply 3 to the 7 times 3 to the 13, you get 3 to the 7 plus 13 power. That is 3 to the 20 power. And if you don't already know that, it's not too hard to see why that works. After all, we're multiplying together 7 threes times 13 more threes. So altogether, that's the product of 7 plus 13, or 23s, all multiplied together. 3 to the 20th power. And when we were dividing, we took 3 to the 16th power and divided it by 3 to the 6th power. And what we ended up with was 3 to the 16 minus 6 power. That is 3 to the 10th power. Now, what does this have to do with logarithms? Where do logarithms come into this? Well, that's what those little blue numbers are. Those are the logarithms, in this case the base 3 logarithms, of the black numbers. So the blue numbers are the base 3 logarithms of the black numbers, which just means that they are the powers that you have to raise 3 to get the black numbers. That's really all logarithms are. Logarithms are just the exponents or powers that you have to raise one number to get another number. Now, we don't have to use base 3 logarithms. We could use base 2 logarithms. And then those would be the powers that you would have to raise 2 to get another number. So here, the black numbers on this list of numbers are all powers of 2. And the little pink numbers tell you what powers of 2 they are. So they are the base 2 logarithms. 2 to the 1 power is 2. So the base 1 logarithm of 2 is, or the base 2 logarithm of 2 is 1. The base 2 logarithm of 4 is 2. The base 2 logarithm of 8 is 3. The base 2 logarithm of 16 is 4, because you got to take 2 to the 4th power to get 16, and so on. We could look at base 10 logarithms. Here, this list of numbers consists of powers of 10, 10 to the 1st power, 10 to the 2nd power, 10 to the 3rd power, and so on. And so these little green numbers are the power that you have to raise 10 to get 10 or 100 or 1,000. They are the base 10 logarithms. So you can have base 2 logarithms, base 3 logarithms, base 10 logarithms, or just about any positive number can work for the base. And we don't have to limit ourselves to positive powers. We can have negative powers or 0 powers. After all, 10 to the 0 power is 1. And 10 to the negative 1 power is 1/10 or 0.1. And 10 to the negative 2 power is 1/100th or 0.01. 10 to the negative 3 power is 1/1000th or 0.001. So the base 10 logarithm of 1 is 0. And the base 10 logarithm of 0.1 is negative 1. And the base 10 logarithm of 0.01 is negative 2. And so on. So logarithms can be positive or they can be negative. Here we're going back to base 2 logarithms. And here I've included some negative logarithms, negative powers of 2. 2 to the 0 power is 1, because any number to the 0 power is 1. It has to be to fit the pattern. 2 to the negative 1 power is 1/2, which in decimal form is 0.5. 2 to the negative 2 power is 1 over 2 to the 2 power, 1 over 4, 1/4, which in decimal form is 0.25. 2 to the negative 3 power is the same as 1 over 2 to the 3rd power. It's 1/8 or 0.125, and so on. And so even if we allow for these negative powers, we can still take advantage of the fact that we can multiply 2 of these numbers together and figure out what we get by adding the logarithms. So for example, if we take the number 0.125 times the number 8,192, do you see what we're going to get? see if you can guess what the answer is going to be before I actually multiply. So what is 0.125 times 8,192? It is one of the numbers on the list. In fact, it's 1,024, which is right there. And notice that comes from, if we take -3 plus 13, we get 10. So 2 to the -3 power, which is what 0.125 is, times 2 to the 13th power, which is what 8,192 is, gives us 2 to the -3 plus 13th power. That is 2 to the 10th power, which is 1,024. Let's try one where we're dividing. What happens if we divide 131,072 by 524,288? Can you guess what we're going to get now? Well, let's see. 131,072 divided by 524,288. And before I hit the equals button, notice that this is the 17th number divided by the 19th number. It's 2 to the 17 power divided by 2 to the 19 power. So it should equal 2 to the 17 minus 19 power. That is 2 to the -2 power, which is 0.25. So yeah, 2 to the 17th divided by 2 to the 19th equals 2 to the -2 power. So the number with a base 2 logarithm of 17 divided by the number with a base 2 logarithm of 19 gives us the number with a base 2 logarithm of -2. What if we want to multiply or divide numbers that aren't on the list? That is, they're not powers of 2 or 3 or 10 or whatever base we're using. Well, we could use a table of logarithms like this that includes not just the whole number powers of 2, but also the numbers in between, the powers that you would have to raise 2 to get 3 or 5 or 6 or 7. So for 2 to the something power to end up being 3, that something is 1.584965 and so on. It turns out that the digits have to keep on going forever if we want it to come out exactly 3, but it's approximately 1.585. So by taking 2 to the 1.585 power, we get pretty close to 3. 2 to the 2.3219 power is how we get 5. 2 to the 585 power is how we get 6. 2 to the 8074 power gives us 7. 2 to the 3 power is 8, and so on. Now, looking over this list of base 2 logarithms, you may notice some of them that look awfully similar to one another. I mean, here we've got 1.5850, here we got 2.5850, 3.5850. Over here I see 4.5850. Is that just a coincidence that they all have the same thing after the decimal point? Well, no, it's actually not a coincidence. The reason it works that way is because, well, the 6 here comes from 3 times 2. So the base 2 logarithm of 6 is the base 2 logarithm of 3 plus the base 2 logarithm of 2. We're adding together these pink numbers to get this pink number. But that means we're adding together 1.5850 plus 1, and we get 2.5850. If we took that, and, well, 12 is 6 times 2. So if we add the pink number, or the logarithm for 6, plus the pink number, or the logarithm for 2, we're adding 2.5850 plus 1, and we're getting 3.5850. 24 is 12 times 2, so adding those pink numbers, or logarithms, we're adding 3.5850 plus 1, and we're getting 4.5850. So notice how when we're multiplying the black numbers, we are adding the pink numbers. When we're multiplying numbers, we are adding the logarithms of those numbers. And we can take advantage of this to take a multiplication problem and turn it into an addition problem. If we have two numbers that we want to multiply together, and we don't want to actually do the multiplication, like maybe we don't have a calculator, and with just pencil or paper, we think adding is easier than multiplying, we can turn this into a problem where all we have to do ourselves is add by, instead of multiplying these numbers together, we can add logarithms of these numbers. We just need to look up these numbers on a table of logarithms. If we're working with base 2 logarithms, like we have been recently, the base 2 logarithm of 47 is about 5.5546. And if we look up 129, the base 2 logarithm of that is about 7.0112. Now, we take those two pink numbers, those two logarithms, and add them together. Add up 5.5546 plus 7.0112, and we get 12.5658. Now we just have to look for a pink number, 12.5658, on our table. There it is, and it corresponds to the black number, 6063. So the number whose base 2 logarithm is 12.5658 is the number 6063, and therefore that's the answer to our multiplication problem. 47 times 129 is 6063. Now this kind of thing came in really handy back in the days before calculators and computers were readily available. Because with the help of a table of logarithms, you can turn a multiplication problem into an addition problem. Instead of multiplying together the numbers you started with, you can look up their logarithms and add those logarithms together. It can turn a division problem into a subtraction problem. Look up the logarithms and subtract those. And it can turn a problem involving finding a power or a root of a number into a problem involving multiplying or dividing that number by something, usually something simple. To see how that works, say for example, we want to know what is the square root of 59,049. That is, what's the number that you square or multiply times itself to end up with 59,049? Well, if we can find that number on a table of logarithms, and here this happens to be base 3 logarithms, the logarithm, the base 3 logarithm of 59,049 is 10. So now instead of finding a number that when you multiply it by itself gives you 59,049, we just have to find a number that when you add it to itself gives you 10. So what number plus that same number gives you 10? Right, 5. And 5 is the logarithm, the base 3 logarithm, for 243. So that's the answer. The square root of 59,049 is 243. We've turned a problem about finding a square root or second root into a problem involving just dividing a number by 2, finding half of that number. So logarithms, as I said, can turn multiplication problems into addition problems. They can turn division problems into subtraction problems. They can turn problems involving raising a number to a power or finding a square root or a cube root or some other kind of root of a number into a problem involving just a simple multiplication or division. And but to do it that way, you have to have just a table of logarithms. And usually the kinds of tables that people would have used for this kind of work would be base 10 logarithms, because that lets you take advantage of the fact that the way we normally write numbers is in base 10, based on powers of 10. And the reason that's helpful is because we don't have to have separate entries in our table for numbers like 3.42, 34.2, 342, and 3,420, because they're all closely related to one another. You can get any one of these numbers times a power of 10 to get another one of these numbers. So if you look at the base 10 logarithms of those numbers, they all have the same thing after the decimal point. The only thing that's different is the number, the whole number part that comes before the decimal point. Now, if I were really explaining to you in detail, so you could actually do it for yourself, how to do calculations with the help of a table of logarithms, it would take maybe a little bit more explaining, but not much more. I'm not going to take the time to do that because, of course, nowadays everybody has access to calculators and computers and phone apps and things like that that will do these calculations for them. So you don't need to resort to looking things up on a table of logarithms. But back in the days before, well, from the time when this method was developed back in the early 1600s by John Napier and Henry Briggs, up until the time when electronic calculators and computers became readily available in the 20th century, this was a really useful thing to know how to do if you were in a profession that involved doing lots of calculations. So, like I said, nowadays, this particular use of logarithms is kind of obsolete. It's not something that really gets used all that much anymore, but it used to be very useful. And if you've ever seen somebody use a slide rule, that's a device that is based on logarithms. Logarithms are involved in how a slide rule works. So back before calculators were readily available, people who did have to do lots of calculations often used slide rules to help them, which were a sort of portable mechanical table of logarithms. So let me make sure we know how the notation works. The base 3 logarithm of 81 is 4. That means 3 to the 4th power is 81. And the way you would write that is you could say that the log to the base 3, that is log with a little subscript 3, of 81 is 4. So that's how you would write the base 3 logarithm of 81 is 4. You'd write log with a little subscript 3, and then 81 equals 4. The base 2 logarithm of 8 is 3, because 3 is the power you have to raise 2 to get 8. So you would write that as log to the base 2 of 8 equals 3. The base 10 logarithm of 0.01 is -2, because that's the power you have to raise 10 to get 0.01. So you would write that as log with a little subscript 10 of 0.01 equals -2. And because base 10 logarithms are so common, if we write log without putting a little subscript, that usually means the base 10 logarithm. So so-called common logarithms are base 10 logarithms. If you see log of a number without the little subscript number that tells you what base it's a logarithm, what base is involved, it means it's the common logarithm or base 10 logarithm. So if you have a calculator with a button labeled log, that's what that button does. It gives you the base 10 logarithm or common logarithm of a number. Now, you should know that some calculators work by expecting you to put in the number first and then push the log button. So this calculator, this is the Windows calculator. I put in the number 0.01, hit the log button, and it tells me that the log of 0.01 is -2. But other calculators want you to push the log button first and then type in the number. So, officially, here's how the notation works. The base 2 logarithm of a number is the power that you have to raise 2 to in order to get that number. The base 3 logarithm of a number is just the power you have to raise 3 to in order to get that number. The base 10 logarithm of a number, otherwise known as the common logarithm of that number, is the power you have to raise 10 to in order to get that number. And in general, the base can be any positive number except 1. So if b stands for any positive number other than 1, the base b logarithm of a number is the power that you have to raise whatever b is to in order to get that number. There's one other special kind of logarithm, special base that's used. If you see ln of x, and if your calculator has a button labeled log, it probably also has a nearby button labeled ln. That is a lowercase l, not an uppercase I. So ln, that refers to what's called the natural logarithm. And that is the base e logarithm, where e is a special number, and I can't tell you exactly what it is because the digits go on forever after the decimal point, but it's approximately 2.818. So the natural logarithm of a number, the base e log of that number, or the ln of that number, is the power that you have to raise e, that is 2.818 and so on, to, in order to get that number. Now, why do we use this base for logarithms? Well, this is something that comes up a lot in higher math, like calculus and above. So in calculus type contexts, this kind of logarithm does come up surprisingly often. So it kind of does require calculus to explain what's so natural about natural logarithms. But trust me, they are sort of the most fundamental kind of logarithm when you get to calculus. Okay, so I've said that logarithms are useful if you're doing calculations without a calculator or a computer, because they turn multiplication problems into addition problems and so on. But nowadays, pretty much everybody has a calculator or something that has a calculator app on it. The fact that you're watching this video pretty much tells me that you have a device like that. So are logarithms obsolete? Is there any reason to care about them anymore? Well, yes, there is. There are other things that logarithms are good for. So what else? Well, like I said, they do come up in higher math, like calculus and above. So if you studied calculus and you didn't have logarithms, or you didn't know that logarithms existed, there would be this big hole or gap in the subject matter of calculus, where it looks like there's something that's supposed to go there, but you wouldn't know what it was. Well, that thing is logarithms. Logarithms come up in scientific and mathematical formulas. So if you're trying to develop a mathematical model, a formula or an equation that describes some phenomenon in science or math, sometimes the best way to describe it, the equation or formula that best fits the data, is one that involves a logarithm. A couple examples that I happen to know of off the top of my head are what's called Benford's law, which is related to the frequencies of the first digits in a list of numerical data. Like, take a list of numerical data, numerical statistics, and count what proportion of the numbers start with a 1 as their first digit versus how many of them start with a 2 or a 3 or a 4. And the prime number theorem, which has to do with how many of the numbers, that is, how many of the whole numbers up to a certain point are prime numbers. There's a formula for approximately how many of the numbers up to any given point are prime, and that formula involves a logarithm. Logarithms are used in things that are measured in logarithmic scales, which includes, a couple of common examples are earthquake intensity measured on the Richter scale. So if an earthquake is measuring 6 on the Richter scale, that actually means it's 10 times as intense as one that measures 5, which would be 10 times as intense as one that measures 4. And sound intensity measured in decibels. That's also an example of a logarithmic scale, where every time the number on the scale goes up by 1, you're actually getting something that increases tenfold. It's 10 times as big as it was before. So thinking about how big numbers are in terms of powers of 10, well, that's a lot like thinking about how big numbers are by talking about how many digits they have. You might talk about somebody earning a six-figure salary. That means if you write out the number of dollars they're earning, it takes 6 digits to do that, and that means that it's somewhere between 100,000 but less than a million. So it's 10 to a power that's somewhere between the 5th power and the 6th power. So the logarithm would be 5 point something. So if you want to, in a way, measuring how big a number is, how many digits it has, or how it compares to the powers of 10, you just look at the base 10 logarithm of that number. And anytime you need to know what power to raise a number to get another number, well, what you need to know is a logarithm. And of course, that comes up if you're working with exponential growth or exponential functions or exponential equations, where the missing number that you're trying to find is the exponent. So if you're solving an exponential equation for a missing exponent, that missing exponent is a logarithm. And so there are situations where you want to know, okay, what power do I have to raise this one number to in order to get this other number? And so that another way of asking that question is, what is the logarithm of this number? Or really, what's the base whatever logarithm of the number that you're trying to get to? Would you like an example? Okay, here we go. Many years ago, the local newspaper published a column where people would write in for advice and information about medical and health-related issues. And one day's column that I cut out included this letter. Somebody wrote in and asked, "Dear Dr. Donahue, I began a running program and I want to do it sensibly. I run 1 mile now. I want to run more, but I would like your opinion of how much more is considered safe. If I stay at the 1 mile mark, I know I won't make much progress." And the doctor's answer? "Yours is a most sensible question. It's safe to increase running distance by 10% each week. Next week, you can run 1.1 miles. The week after, go for 1.2 miles. I wanted to calculate how long it would take you to reach marathon mileage, but it gave me a headache." Well, it makes me a little sad that a doctor isn't good enough at math to figure something like that out without getting a headache. But it's not that difficult a question. So let's figure out what the answer is. How many weeks would it take to reach marathon mileage if you increase your distance by 10% each week? So that means that the first week you add on 10% of 1 mile, which would be 0.1 miles. So that means you're running 1.1 miles that first week. Then the second week, you add on 10% of 1.1, which would be 0.11. That brings you up to 1.21. Now, Dr. Donahue said 1.2, and either he made a mistake or maybe he just rounded off. But we're not going to round off. We're going to keep all the decimal digits. And so the next week, if we add on 10% of 1.21, we would be adding on 0.121, bringing us up to 1.331. Then if you add on 10% of that, that means after the fourth week, you're running 1.4641 miles. Add on 10% of 1.4641, and that brings you up to 1.61051. And if we can continue in this pattern, the question is, how many weeks does it take before the number of miles you're running reaches marathon distance, which is a little over 26 miles. It's about 26.2 miles. So the pattern here is that each week, this week's distance is going to equal last week's distance, that is 1 times d, plus 10% of last week's distance, 0.10 times d. If we add those together, we just get 1.10 times d. So each one of these numbers is just the previous number times 1.1. 1 times 1.1 gives you 1.1, times 1.1 gives you 1.21, times 1.1 gives you 1.331, times 1.1 gives you 1.4641, and so on. So after n number of weeks, the distance that you would be running would be 1.10 to the nth power. So the question now becomes, what does n have to be so that 1.1 to the nth power is equal to 26.2? Now we could just find this by trial and error, or by calculating 1.1 for all the different numbers until we get a value that reaches 26.2. And in the context of this particular problem, it really only makes sense for n to be a whole number, because we're increasing it each week. But let's figure out what n has to be exactly. It probably won't come out to be exactly a whole number if we want 1.1 to the nth power to reach exactly 26.2, but what would it be? Notice this is a question about what power do I have to raise 1.1 to get 26.2. So that is, what is the base 1.1 logarithm of 26.2? What is log to the base 1.1 of 26.2? Okay, so how would we calculate something like that? If you have a fancy calculator, it might be able to directly give you the log to any base of any number. But lots of calculators only have a log button for base 10 logarithms and an ln button for base e logarithms, but they don't have a button for any other base logarithms. And what we want here is a base 1.1 logarithm. So how do we calculate that? How do we find a logarithm that isn't just a base 10 logarithm with the help of a calculator that just has an LOG button? Well, there is a formula that lets us convert from one base to another. And according to that formula, the base b logarithm of any number x is equal to the common logarithm of that number divided by the common logarithm of the original base. Now, actually, we wouldn't have to use common logarithms. We could use any other base. So this formula can be used to convert from any base logarithm to any other base logarithm. But it's particularly useful if you have a calculator with an LOG button to convert to common logarithms. So that means to calculate the base 1.1 log of 26.2, we can get our calculator and ask it for the common log of 26.2 divided by the common log of 1.1. So let's work that out. Let's see what that gives us. So this calculator wants me to punch in the number 26.2 and then hit the logarithm button. So there's the log of 26.2 to the base 10. And then we want to divide that by the log of 1.1. And when I hit equals, there's my answer, 34.4235. So it's about 34.4 weeks. So after 34 weeks, we haven't quite reached 26.2 miles, but then week after that, the 35th week, we would be. So 1.1 to the 34 power is 25.5 something. So if we continue in this pattern, by the 34th week, we'd be running 25.5 some miles. And then the week after that, we add on 10% of that, which brings us to 1.1 to the 35 power, which is, now we're above marathon distance. We got up to about 28.1 miles. So the exact power of 1.1 that hits 26.2 is somewhere in between 34 and 35. We saw it was 34.4 something. So that's an introduction to logarithms and what they are and why we care about them. If you have any questions that I haven't answered in this video or comments about anything I've said, feel free to leave a comment. And I hope you found this helpful and interesting, and thanks for watching.